Hello, we're going to try something different for this video today. I'm going to try a different application, see how it works out. This is going to be your review sheet for your probability and statistics exam. So let's get right into it. I can prepare for my probability statistics test by practicing. So let's go. Chloe the Cardinal. The probability that Chloe the Cardinal shows up in the Schlansky's backyard is 12/19. The probability that Chloe shows up in the Silverman's backyard is 10/17. If the probability that Chloe shows up in the Schlansky's backyard or the Silverman's backyard is 12/16, what is the probability they show up in both? Or, whenever you see or, we have a song. It's asking for both being and. P of A and B equals P of A plus P of B minus P of A or B. These two could be interchanged depending on which one you're finding. If you're finding and, then put and there. If you're finding or, you'd put or there. So we're trying to find P of A and B. We'll let Schlansky be A and we'll let Silverman be B. So that's going to be 12/19 plus 10/17 minus P of A or B, which is 12/16. From here, you're just going to type that into the calculator. You'll get your answer. I don't know if I can pull my calculator up with this. That's the only problem. 12/19 plus 10/17 minus 12/16. I got P of A and B equals 607/1292. In general, you always want to leave it in fraction form. It's a 7. In general, you always want to leave it in fraction form unless it specifies otherwise. Okay. Number 2. So number 2 is the same thing as number 1. I'm not going to go over it with you. It's the same procedure. I'm just going to pretty much go over the odds. All right. On a given school day, the probability that Nick oversleeps is 48%. Let's call that A. And the probability that he has a pop quiz, let's call that B, is 25%, assuming that these two events are independent. Well, independent is P of A and B equals P of A times P of B. Yeah, it's asking that he oversleeps and. So it's asking for P of A and B. P of A is 0.48. P of B is 0.25. I can pull that up on the calculator. Let's see if this lets me do that. 0.48 times 0.25 is 0.12. Oh, I guess I lose that. That's annoying. So your answer is 0.12. That's it. So if it's asking you for and, there's two possibilities. If it says that they're independent, or if it doesn't say independent. If it says independent, then P of A and B equals P of A times P of B. If it doesn't, then P of A and B equals P of A plus P of B minus P of A or B. So that's the tricky part about and. There's two different formulas to use depending on if it says independent or not. And then or, there's only one formula. It's the same as the and formula. It's just the and and the or are switched. P of A or B equals P of A plus P of B minus P of A and B. That's it. All right, let's move on. To number 4. Whenever you have a two-way table, you need to do your totals. So I'm going to add all the totals up. 4 plus 37 plus 68 is 109. 6 and 25 is 31, and 87 is 118. 25 and 47. I'm just going to use my calculator to do that. 25 plus 47 plus 157 is 229. 4 and 6 and 25 is 35. That's a little too ugly for me. Let's try that again. 37, 25, 47 is 109. And then 68, 87, 157 is 312. To get my total, I can either add up those or add up those. They should add up to the same thing. You can do it both ways to make sure. And I got 456. The person, so it's asking what is the probability that the person texts over 50 messages per month, given that the person is between the age of 23 and 60. You always want to ask yourself, is there a condition? The condition always comes after the phrase given that. So if the condition is that they're between 23 and 60, I'm going to circle between 23 and 60. I'm only looking at this row. So out of the 229 people that are between 23 and 60, how many text over 50 messages per month? 157. It's a little sloppy, so let's just rewrite that. 157 over 229. The person is 15 to 18 and texts 11 to 50 messages per month. Is there a condition? No. All right, it's not something only look at certain people. It's just saying out of everybody, how many are between 15 and 18 and text 11 to 50 messages per month? That's there. And because there's no condition, the total is your denominator. The person texts 0 to 10 messages per month. There's no condition. All it's talking about is the person texts 0 to 10 per month. Well, 35 out of the total. The denominator is always your total unless there's a condition. If there's a condition, circle the condition, and that becomes your denominator. Four is the same type of thing. 5 is very similar, but now we're going to create our own. The guidance department, whenever we're dealing with probabilities, we want to create a two-way table. So when we're creating our own, we want to take a look at the things that are involved. There's Key Club and there's AP Physics. So one axis is going to be Key Club and not Key Club, and the other one is going to be AP Physics and not AP Physics. Whenever you're making a two-way table, You always want to make one axis yes and no for one thing, the other yes and no for the other thing. Now, because these are percents, my total is going to be 100. Whenever you have percents with probability, the total is 100. So 2.3% are members of Key Club. It doesn't say anything about AP Physics in that 2.3%. It just says that 2.3% are members of Key Club. Therefore, the total for Key Club is 2.3. 8.6% are enrolled in AP Physics. It doesn't say anything about Key Club. The total for AP Physics is 8.6. 1.9% are in both. Well, both meaning Key Club and AP Physics. So at this point, I want to fill in the rest of my 2A table. So I'm just going to subtract and add everything to find the missing pieces. I'm going to use my own calculator that I have here. I don't think you need to see my subtraction. I subtracted 8.6 and 1.9. I'm going to subtract 100 and 8.6. That gives me 91.4. I'm going to subtract 100 and 2.3. That gives me 97.7. I'm going to subtract 2.3 and 1.9. That gives me 0.4. And then I'm going to subtract 97.7 and 6.7. And that's 91. So let's see what the question's asking. Determine the probability of P given K. Given. Whatever comes after given is your condition. So given K, I circle my K. Those are the only numbers I'm looking for. What's the probability of P given K? Well, 1.9 over 2.3. It's asking for the nearest tenth of a percent. So I go to my calculator and I'm going to lose this when I do that. So I'm just going to use my own calculator. I do 1.9 divided by 2.3. I get 0.8260 ... It wants the nearest tenth of a percent. So I multiply it by 100 and I get 82.6%. The principal would like a basic interpretation of these results. So let's get my text going here. So since the condition is Key Club, 82.6% of the members of Key Club are enrolled in AP Physics. And that's it. I'm sorry, 82%. 82.6% of seniors in Key Club are enrolled in AP Physics, just because this particular question, this whole situation is based on seniors. So if they don't give you a 2A table, you make your own 2A table. And when you make your own 2A table, just one axis is one thing and then not that. The other axis is the other thing and then not that. Your axes are yes and no for each thing. And then you just fill in from there. If there's percents, then your total is 100. If not, then you just have to go by the information they give you. All right. 6 is the same type of thing. Let's take a look at 7. Independent. So there are 2 methods for independent. I'm going to keep things simple and stick with one. And we talked about it before. P of A and B equals P of A times P of B. Yeah. That's your formula for independent. So let's fill in my totals like we talked about before. Whenever you're dealing with a 2A table, fill in your totals. Let's choose values for A and B. Let's have A, it says gender and type of payment. So let's just pick a gender and let's pick a type of payments. Let's go credit card. So the probability of mail and credit card is 40 over 125. Mail, probability of mail is 50 over 125. Probability of credit card is 100 over 125. The good thing about this formula is the denominator is always the total. That's what makes this easy. Now I'm going to type in the left-hand side and the right-hand side. I'm going to see if they're equal or not. I think I'm going to lose this when I go to type it in, but let's type it. I want you to see it. So 40 over, actually, can I do this? I don't know if this is working or not, but it might. So let's do 40 over 125. 40 over 125. That's my left-hand side. My right-hand side is alpha y equals enter. 50 over 125 times 100 over 125. 8 over 25. So they're both 8 over 25. So this is 8 over 25, and this is 8 over 25. So since they're the same, are they independent? Yes. They are independent because P of A and B equals P of A times P of B, yeah. Now you could also do this using the other independent formula, which I'm not going to do right now. That's P of A equals P of A slash B. That's it. I prefer this one. It's easier. The denominator is always your total. So for the most part, I like to go with that. When you learned it, if you like this one better, then go for that one. So let's move on from independent. Independent is a very important question. Every single Regents, they ask about that. And that brings us to our key phrase, normally distributed. Whenever we see normally distributed, we go to our calculator, we do normal CDF. So we're going to do normal CDF. That's second vars. So let's pull our calculator back up. So I'm going to go to second vars, which is distribution, normal CDF. So now I need lower, upper, mu, and sigma. Lower, upper, mu, and sigma. So it says that the mean is 7.1. That's mu. It says that the standard deviation is 1.4. That's sigma. It says between 5 and 8. That's my lower and my upper. So my lower is 5. My upper is 8. My mu is 7.1. My sigma is 1.4. And I get 0.673 dot, dot, dot. Now there's three possibilities. I could just leave it. I can multiply it by 100 for a percent, or I can multiply by the number of data points if it gives me the number of data points. So what's the question asking, or the first question asking? To the nearest percent. So I'm going to multiply by 100, and that's going to give me 67%. Now it's asking me another question. So again, I'm going to do lower, upper, mu, sigma. My mu and my sigma don't change. My mu is 7.1. My sigma is still 1.4. Now it says less than 5 hours of sleep. If it's less than 5, it could be 5 and lower. So my lower is 0, my upper is 5. Let's pull my calculator back up. Second vars, second vars, normal CDF, keep my thing on PDF. Quit. Second vars, normal CDF. My lower is 0. My upper is 5. My mu is 7.1. And my sigma is 1.4. 0.0668 dot dot dot. Now again, there's 3 possibilities. A, I can leave it like this. B, I can multiply by 100 for a percent. Or C, I can multiply by the number of data points if they give me a number of data points. In this case, they're giving me the number of data points. They're giving me their 2,500 employees. So I'm multiplying that by 2,500 times 2,500. And I get 167. Approximately how many of them? 167. That's it. These are really easy questions, the normally distributed questions, as long as you know how to do them. It's just all in the calculator. It's a few buttons you press. And once you get your answer, again, you multiply by 100 if it's a percent. You multiply by the number of data points if they give you the number of data points, or if it just asks for a probability, you could leave it as a decimal. Now, if it said more than 5, instead of less than 5, let's just take a quick look at that. If it said more than 5, then my lower is 5, and my upper, we said, is 9 and 9 and 9, 9, 9, 9, 9. Just some giant number. It'll get close. It'll never, ever reach. That's your upper bound. If it says more than, if it's less than, then you can go to 0. Really important. Every Regents, they ask that type of question, and it's really an easy question as long as you know how to do it. It's another one right there. All right. Ricky and Marissa are very competitive with each other. Ricky took a physics test where the mean was 82. So for Ricky, the mean, let's use the other symbol. Remember, mean has 2 symbols, x bar and mu. Let's leave it as mu. So mu is 82. Standard deviation is 4. And his score, let's call it x, is an 85. Marissa took a chemistry test, so they're in different classes, so you can't really compare this data directly, where the mean was 78, standard deviation was 6, and she got an 83. Who scored better? When you're comparing 2 separate events, you need to find the z-score. Z-score is x minus mu over sigma. So for Ricky, it's 85 minus 82 over 4. And for Marissa, it is 83 minus 78 over 6. You can use a calculator. I'm not going to pull it up for this. It's simple enough to type in. That's going to give you 0.75. This is going to give you 0.83. Who has a higher z-score? Marissa. Marissa Feed costs. She has a higher z-score. So whenever you're comparing two separate events and you want to know who did better, you find the z-score. Z-score is x minus mu over sigma, where x is the test score, mu is the mean, and sigma is the standard deviation. All right. Are we almost done with probability? I think we're almost done with probability. I think we're almost up to statistics. Yeah. All right. So that's why I wanted to do this whole thing in Zoom, because I wanted to talk to you about statistics. It's a lot of talking. And whenever I review it, now, we do read and review, it's just like 10 minutes of me talking. So there are 3 types of statistical studies. There are surveys, observational studies, and controlled experiments. A survey is when you ask somebody something. You're asking their opinion on something. You're physically asking them, whether it's verbally, on paper, you're asking somebody a question. An observational study is where you're observing the results of something without actually interfering. Whereas a controlled experiment is where the person performing the controlled experiment is physically applying a treatment. That's the main difference between a controlled experiment and an observational study. In a controlled experiment, there's a treatment involved. The researcher is actually giving the participants something. So for example, if I want to see if smoking during pregnancy leads to low birth weights, I'm going to do an observational study. I'm not going to give these pregnant women cigarettes and say smoke them so I can see if it causes something. I'm just going to look at the data. I'm going to look at the results of women who did and did not smoke during pregnancy and compare the birth weights. That's an observational study. I'm observing the results. I'm not actually giving these poor women cigarettes. In a controlled experiment, that's where we'll talk about that in more detail in a moment, but that's where I'm actually giving them a treatment. So let's start by talking about surveys. When you're performing a survey, I'm sorry, one more thing I want to talk about before that. Out of the 3 statistical studies, the only one, so they all can lead to correlations in data. They could all lead to relationships in data. The only one that can lead to a causal relationship is a controlled experiment. So if I want to say that smoking during pregnancy causes low birth weight, I have to do a controlled experiment. If I do an observational study, I can say there's a relationship between, there's a relationship or a correlation between smoking during pregnancy and low birth weight. But if I want to say that it causes it, the only way to achieve a causal relationship is a controlled experiment. So let's talk about each. A survey, you're asking people something. So you have to determine what the population is. Let's say I want to know how students in Westbury High School feel about soccer. The population is students at Westbury High School. Now, I'm not going to be able to ask every single person in Westbury High School for various reasons. One, we can't even go to Westbury High School right now. So I'm going to choose a sample. So the sample should be random, not bias. Bias would be having my sample be the soccer team. If I ask the soccer team, they're all going to say they like soccer. And then my sample is going to tell me that 100% of the population like soccer. That's not the case. An unbiased sample should be random. Every 5th person walking into school, every 10th person walking down Old Country Road or on Jericho Turnpike, whatever it is. You want it to be random. Every member of the population has to have a chance of being chosen. I can't say my sample is going to be AP Calc kids, because not every student is in AP Calc. I can't even say it's going to be 9th grade English classes, because if it was 9th grade English classes, then I'm not including 10th, 11th, and 12th graders. So every member of the population has to have a chance of being chosen, and we want it to be more than 2 or 3 people. We want it to be a good enough sample. There's no real percent that you need to know that you have to give, but it should be a reasonable amount of people that you're asking. You shouldn't be just asking 5 people. Now, the point of doing a survey is the sample statistic represents the population characteristic. What that means is, so let's say I did my random sample. I did every 5th person walking in the building in the morning until, noon, because that's when you guys start coming to school. And I found that 40% of my sample, 40% of the people I asked like soccer. From that, I can conclude that approximately 40% of the entire school, of everybody in the school, likes soccer. That's the point of doing a survey. My sample is supposed to represent the population. And if I don't choose a good sample, then it's not going to represent the population. If I choose if in reality the population characteristic is 40% like soccer, if that is the actual value, if I choose people on the soccer team, I'm not going to get 40%. I'm going to get 100%. If I choose students in the drama club, it's going to probably be like 5 or 10%, because in general, students who are into drama aren't as into sports. Those are not good samples because they don't represent the entire population. You want to get every 10th person walking in the building. You'll get some drama kids, you'll get some soccer players, you'll get some band people, you'll get some AP Cal kids. It's a mix of everybody, and that's what you want when you're doing your sample. Not too much to talk about an observational study. We talked about it before. You're just observing data, and then you're making conclusions based on that. Now, within observational studies, I started talking about sample distribution. So sample distributions are really, 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 really important. If I want to know if we have an expected value, if a value is expected or usual, all right, I went to Chipotle to get dinner, and I was online for 15 minutes. And I was like, this is horrible. This is not right. I was online for too long. And they would tell me that, I'm sorry, this is not expected, this is unusual because it's too busy right now. And if I want to determine if that was usual or unusual, expected or unexpected. To determine if something is usual or unusual, expected or unexpected, you need to find the confidence interval, the 95% confidence interval. To find the confidence interval, it's the mean plus and minus 2 times the standard deviation. The term margin of error is just 2 times the standard deviation. That's how far from the mean I will have as far as an expected value goes. So I do the mean plus 2 times the standard deviation. I do the mean minus 2 times the standard deviation. And then those 2 values is my range of values of expected values. So if I want to know if a coin is fair, if I'm flipping a coin and I got like 5 heads in a row and I want to say, well, what's going on here? There's something wrong with this coin. If the theoretical probability is in the confidence interval, then yes, because the theoretical probability is an expected value. If the theoretical probability is outside the confidence interval, then it's not fair because it's not an expected value. The theoretical probability of doing something, if it's fair, should be inside that confidence interval. Which brings us to controlled experiments. 2 key phrases. When you're doing a controlled experiment, you are randomly selecting a sample, and then you are randomly assigning half to a treatment group, half to a control group. So I always say, okay, so let's say I want to do a controlled experiment. I got some vaccine I cooked up in my basement for COVID-19, and I want to see if it works. So I'm going to randomly select a sample of the population. So I'm going out in Westbury, and I'm picking every 10th person walking down Jericho Turnpike. So I took them, I put them in a line, and now we're walking over to the high school. And we go into the gym. So now I got this sample that I randomly selected. Now I'm going to randomly assign half of them to the treatment group, half of them to the control group. So I'm going to go 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. All 1s over on this side, all 2s over on that side. This will be my treatment group. This will be my control group. I won't tell them that. So you go over there, you go over there. I go to my treatment group and I give them that drug, that vaccine that I cooked up in my basement. And then I go to the other group and I give them something that looks the same as that, and maybe it's just full of sugar. There's no drug in there. I send them home. A month later, I analyze the data of who got it and who didn't get it. That's how you perform a controlled experiment. All right, randomly select a sample, randomly assign half to a control group, half to a treatment group. apply the treatment to the treatment group, give the control group a placebo if possible, then we analyze the data. So how do we analyze the data? Well, the first step is to find the mean difference. I'm going to find the mean of the treatment group, the mean of the control group, and subtract them. So maybe 20% of them got sick and 30% of them got sick. So the mean difference would be 10%. I would subtract them. Is that significant? Is that significant, or is that a difference due to random chance? Well, to determine that, I now re-randomize everybody. I take all the people and I kind of just mix them all together, and now just randomly picking half, whether or not they got the treatment or not, and putting the other half there, find the means, subtracting them. We do this through simulations most of the time, through computer simulations, doing that many times. So now I have a sample distribution. If my mean difference is outside the confidence interval for that sample distribution, then the treatment is effective, because I shouldn't have gotten that big of a difference if it was just randomly choosing people. If my mean difference is inside the confidence interval, then I would have gotten that value just randomly picking half the people and not half the people without giving anybody necessarily a treatment. So that would not be a significant value. So again, to determine if a treatment's effective, find the mean difference, re-randomize everything, do a simulation, get a sample distribution. In order for the treatment to be effective, in order for it to be a significant difference, the mean difference must be outside the confidence interval. If it's not effective, if there's not a significant difference, then the mean difference is inside the confidence interval. So that's not the last time you're going to hear the whole little spiel about statistics. It's a lot of understanding. The math itself is simple. It's just about understanding all of those things, which is why we just have to keep on talking about it and doing these controlled experiments and these observational studies and these surveys for it to make sense. All right, so I got to drink a little bit more water, and then we're going to go back to some questions. A study is, I can probably type on this thing, right? A study is done. So it's asking if it's an observational study or an experiment. A study is done to see how high soda will erupt when mint candies are dropped into a 2-liter bottle of soda. You want to compare using 1 mint, 5 mints, 10 mints. You design a cylindrical mechanism, blah, blah, blah. You have 15 bottles of soda. You randomly assign 5 bottles into which you drop 1 candy. There it is right there. That's my answer. You drop 1 candy. You drop 5 candies. You drop 10 candies. You are applying a treatment. Therefore, it's a controlled experiment. Controlled experiment because you are applying a treatment. You're applying a treatment. You are putting these mints inside the soda. You want to see if 5th grade boys or 5th grade girls are faster at solving Ken puzzles. You randomly select 20 5th grade boys and 20 5th grade girls from 5th graders in your school district. You time and record how long it takes each student to solve the same Ken puzzle. Are you applying a treatment? Are you giving these 5th graders pills to help them do these things faster, or sugar or energy drinks? No, you're just letting them do these puzzles and you're sitting back and watching. That's an observational study because there is no treatment being applied. In A, there was a treatment. The researcher put mint candies inside a bottle. That is applying a treatment. In B, the researcher didn't do anything. He just sat back and watched these kids do puzzles and saw how long they took. That's the difference between a controlled experiment and an observational study. And again, the only way to get a causal relationship is a controlled experiment. They can all lead to relationships and correlations, but only controlled experiment can create a causal relationship. We'll take a look at it. Supposing your health class, you read 2 studies on the relationship between eating breakfast and success in school. Both studies concluded that eating breakfast causes, come on, there we go, elementary school children to be successful. Suppose that one of the studies was an observational study. Describe how you would recognize that they had conducted an observational study. So I'm going to say that no treatment was applied. Were the researchers correct in their causal conclusion? No. Observational studies can lead to correlations and relationships, but cannot create a causal relationship. Suppose that one of the studies was an experiment. Describe how you would recognize they had conducted an experiment. Well, an experiment, they would have randomly selected a sample of school children. They would have randomly assigned half to a control group and half to a treatment group, and then they would have applied the treatment, which is giving breakfast to the treatment group. Were the researchers correct? Being how both studies concluded, I mean, if there was a significant difference, if the mean difference was outside the confidence interval, then I would say yes. Controlled experiments can create causal relationships. Boom. It's a long video. Hope you're enjoying it. All right, let's go through this. The following is an example of a sampling distribution of sample proportions. The mean is 0.4955. The standard deviation is 0.0852, and it says there's 40 flips. Find the margin of error. So margin of error is 2 times the standard deviation. So it's 2 times 0.0852. 2 times 0.0852 is 0.1704. What is the meaning of the confidence interval? Oh, it's asking for the margin of error and the confidence interval. All right, so now the confidence interval equals the mean plus and minus 2 times the standard deviation. So it's going to be 0.4955 plus 2 times 0.0852 and 0.4955 minus 2 times 0.0852. I'm going to use my calculator for that. 0.4955 plus 2 times 0.0852 is, ow, I just banged my elbow. That felt really nice. 0.6659, and then minus 0.3251. So that makes my confidence interval, always go for your smaller one first, 0.3251, 0.6659. Explain the meaning and the context. I am running out of space, man. It is expected that the proportion of heads is between 0.3251 and 0.6659. So basically what that means that if I'm flipping this coin 40 times, I'm going to expect that my proportion of heads is going to be about 32% to about 67%. What does the sample mean? What does the population mean? How do they compare? I can probably type this. The sample mean is the mean from the sample, which we said was 0.4955. The population mean, well, that's the theoretical probability. What's the probability of getting heads? It's 1 out of 2, which is 0.5. All right, the population mean, there's 2 possibilities. There's heads and tails. There's 1 heads, 1 out of 2 is 0.5. So how do they compare? They are approximately the same. The sample mean and the population mean should approximately be the same. Is the coin fair? Well, the coin is fair if the theoretical probability is inside the confidence interval. So my theoretical probability is 0.5. There's my confidence interval. Is my theoretical probability inside the confidence interval? Yes. So I'm going to say yes. Yes, the theoretical probability 0.5 is inside confidence interval. Fred flipped a coin 40 times and 65%. Oh no. Oh, that was scary. Oh no. Undo that? Yes. All right, I'm leaving that mark. I'm over it. Fred flipped the coin 40 times and 65% of the flips came up heads. Is this an expected outcome? Well, is 65% inside the confidence interval? Yes, barely, but if it's inside, it's not like, oh, it's close. If it's in, it's expected. If it's out, it's not expected. So I'm going to say yes. 65% is inside confidence interval. If the experiment was performed where the coin flipped 20 times, how would the data be affected? So this was the result from 40 flips. As the sample size decreases, the mean relatively stays the same. The standard deviation increases. You want a larger sample. As you increase the sample size, the standard deviation gets smaller. All the data gets tighter together. When you have less samples, then this data is spread out more. Think of it this way. If I flip a coin twice, am I going to get some zeros? Yeah, it's very easy to flip a coin twice and get 2 tails. If I flip a coin 1,000 times, am I going to get 0 heads? It's not going to happen. All right, I'm not going to get those values all the way out here at 0 and 100. I'm going to get tighter and tighter to 50. So as sample size decreases, that's bad. We don't want it to decrease. As sample size decreases, the data is going to spread out more. So the standard deviation increases, but the mean relatively stays the same. It's going to relatively stay close to the theoretical probability. All right. How is that thing still there? I don't know what's going on. All right. Bias. Again, we said that bias is bad. Bias is asking the soccer team if they like soccer to see how the whole school feels about it. All right. If there's a pre-existing reason to believe someone's going to feel a certain way, that's bias. The opposite of bias is random. So, which is least likely to contain bias? So is it asking for a good answer or a bad answer? Least likely to contain bias. It's asking for a good answer. It's saying we don't want bias. Surveying a sample of people leaving a movie theater to determine which flavor of ice cream is the most popular. Is there a reason that people who go to the movies necessarily like chocolate ice cream as opposed to vanilla ice cream? No, this is good. All right. Just because people go to the movies doesn't mean they're going to feel a certain way about ice cream. Surveying the members of the football team to determine the most watched TV sport. Well, if I ask people on a football team what sport they watch, they're probably going to say football. That's biased. It's not random. I'm asking people that I know are going to say they like football. Surveying a sample of people leaving a library to determine the average number of books a person reads in a year. Is that bias? Yes, people at the library, they go there for books. People at the library read books. That's bias. People that don't go to the library, people that don't read, aren't going to the library. So I'm not getting any people that read nothing. I'm one of those people. I don't really read. But that's the example of bias, all right? You can't ask people at a library to determine how the whole population feels about reading, all right? People at a library read more than most people. Surveying a sample of people leaving a gym to determine the average number of hours a person exercises per week. If they're at the gym, then they're probably exercising a lot. That is bias. You can't ask people that you know are working out how much they work out. A lot of you don't work out whatsoever. You wouldn't be included in that. All right, that's bias. There's no bias in choice one. Because people go to the movies doesn't mean that they necessarily like chocolate chip ice cream. There's no correlation between them. There's no bias there. It's random. It's the same type of thing. I don't want to go over it again. Let's take a look at number 6. Elizabeth waited 6 minutes. I'm going to skip down to the end. Was Elizabeth's wait time unusual? To determine if something is usual or unusual, you need to find the confidence interval. That's the understanding you need to have to determine if something's usual or unusual, expected or unexpected. Find the confidence interval, which is the mean plus and minus 2 times the standard deviation. I said it before, both x bar and mu, both of these mean the mean. So it said that the mean was 226 plus and minus 2 times the standard deviation was 38. So it's 226 plus 2 times 38, 226 minus 2 times 38. You can use your calculator. That's what I'm going to do. 226 plus 2 times 38 and minus, I got 302 and 150. That's my confidence interval. What's my value? Now be careful, there's a little twist here. 6 minutes. These are all in seconds. So 6 minutes is 360 seconds. Is 360 inside the confidence interval? No. So was it unusual? Yes, because 360 is not in the confidence interval. All right, let's keep on rolling along. 7. All right, so 7, this is where we're going into like the 4-point sample distribution questions now. I think these are like the easiest 4-point questions you can get on any of the regencies. So let's take a look. Again, I'm just going to kind of skip ahead here. It says, based on the simulation, what is a plausible interval? Containing the middle 95%. It's asking for the confidence interval. So again, the confidence interval is the mean plus and minus 2 times the standard deviation. There's my mean, there's my standard deviation. 0.254 plus 2 times 0.060. 0.254 minus 2 times 0.060. Use your calculator. 0.254 plus 2 times 0.060. 0.374, 0.134, 0.134, comma 0.374. A student found that 18 out of 50 candies were blue. Use statistical evidence to explain why this is an expected value. Well, 18 out of 50, let's find out what that is as a decimal, since everything is in decimal form. 18 out of 50 is 0.36. To determine if that's an expected value or not, we need to see if that's inside the confidence interval. Is 0.36 inside the confidence interval? Yes, it's between 0.134 and 0.374. So 0.36 is inside the confidence interval. When it comes to Regents review time, this is like the easy, make sure everybody can do this. It's not complicated. It's just a little formula for confidence interval. And then either yes, it's inside, or no, it's not inside. All right, so that's the same thing. Describe a controlled experiment. Again, for controlled experiment, we are going to randomly select a sample of people with the common cold. No, I'm not going to take shortcuts. People with the common cold. Then I'm going to randomly assign half to a control group and half to a treatment group. I'm going to give the treatment group the pill and give the control group a placebo, and then I'm going to analyze the data. And again, analyzing the data, that's where we're going to find the mean difference, re-randomize everything, and then see if my mean difference is inside or outside the confidence interval. But that's not part of this question. It just says to design it. That's how we design it. All right. Same thing. 11. Blah, 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 blah. Calculate the mean difference. Group 1 minus group 2. So my means are right here. My mean difference is 80.16 minus 83.8. I use my calculator. I get negative 3.64. Explain its meaning in the context of the problem. On average, students in group 1 scored 3.64 points lower than students in group 2. That's all it means. It means on average, whatever happened in the first group is this much higher or lower than the second group. Because it's negative, that's why it's lower. Is that a significant difference? Does that mean that I really want to go with group 2, or did that just happen due to random chance? I don't know if it's a significant difference just by finding the value alone. So to determine if it's a significant difference, I'm going to re-randomize everything, which it's saying it's doing. So I'm re-randomizing all these students. I'm throwing them in one big pile, and I'm just randomly, after this already happened, I'm picking half out. I'm recording their values. The other half, I'm finding the mean difference. I'm making a sample distribution. Now I'm looking at my negative 3.64. All right, this is where this gets a little tricky. Let me see if I can blow this thing up. Can I blow this thing up? I'm going to try. I'm going to try. I'm going to try. Yeah. All right. Let's just get rid of everything else. So negative 3.64. Oh, let's make it even bigger. Yeah. Negative 3.64 would fall like right there. So I have two bars that are more extreme than negative 3.64 approximately. So I have this bar right here. That looks like it's at about 6. And this bar right here looks like it's at about 3. So together, 3 and 6 is 9. 9 out of how much? How many simulations were there? 9 out of 500. So 9 out of 500 is 0.018. To make that into a percent, 0.018 is 1.8%. What's the magic number for confidence interval? The magic number is 5. Whoop, too close. 5%. If it's less than 5%, it's outside the 95% confidence interval. So since 1.8% is less than 5%, the treatment was effective. So yes. There is a significant difference because negative 3.64, you can just say is outside the confidence interval, or you can say negative 3.64 occurred in less than 5% of the simulations. Cool. That's it. The math itself is pretty simple. Conceptually, there's a lot to this, but you know, it just, you find the mean difference, you re-randomize everything. If the mean difference is outside, then yes, the treatment was effective. It's a significant difference because I wouldn't have gotten that value randomly. So because I got such a large difference, it's because the treatment made such a large difference. If it's inside, I would have just gotten that difference randomly. Therefore, that wouldn't be effective. In this case, the mean difference is outside the confidence interval. That means that the treatment was effective. And I think we got, what, one more type of question to take a look at? That's the same type of thing. It's asking me for a exponential regression equation. All in the calculator. Stat edit. Stat calc. 0. Xbreg. So I'm going to pull up my calculator. I'm gonna move me. Hi. Stat. Oops, let's turn it on first. Stat edit. -20. -10. 0. 10. 20. 30. 40. 1, 2, 5, 9, 17, 29, 50. Second quit. Now I go back to stat, calc, option 0 is expreg. Hit enter a few times or tab down. It's telling me my values. Remember this, y equals a, b, that's supposed to be y equals a, b to the power of x. It says to round to the nearest thousandth. So a is 4.194. B is 1.068. So it's y equals 4.194, 1.068 to the power of x. Don't read ahead with these questions. Just take it one piece at a time. The first question ended right here. Now, using this equation, predict the amount of blah, blah, blah. It's giving me this value, 50 degrees Celsius. Degrees Celsius is x, so this is basically saying that x is 50. So now I'm going to substitute x with 50. So 4.194, 1.068 to the power of 50. Notice that this question says nearest tenth, this one says thousandth. You need to read very carefully. The different questions within the same problem may ask you to round to different values. So let's pull up my calculator again. And we've got 4.194, 1.068 to the power of 50. To the nearest tenth is 112.5. There's obviously a lot in probability statistics. I really don't think I think that difficult. I really think that the math itself is really simple. It's just knowing all the concepts. It's just practicing and knowing how to do all the different types of questions. It's knowing your probability formulas. It's knowing how to do your two-way tables. It's knowing how to do your normally distributed. It's knowing how to find confidence interval. It's just knowing how to do all these little things, which comes through practice. I don't think there's anything that's really hard that we did. It's just a lot, which means you need to practice. So practice, use this video. It's been a lot. I'm afraid to see how long. I feel like it's probably been like an hour. Use this video, practice, and do well on your test. And this is, again, a big topic on the Regents. They ask a lot of points on probability statistics, and this is where you're going to rack up a lot of points. All right, that's it. Practice. Hopefully this worked, or else I'm going to be very, very angry. Bye.